Okay, I think now the recording is on. Um, okay, good. Let me share my screen. Um, do you have any questions about the things we did last time or the time before? Can you hear me?
Yes, we can hear you.
Okay.
But are you talking about probabilities or this class? Because this one is the
Mm,
first one.
yeah, that's actually not true in the sense that it's just, I mean, I think it's the same teacher that you have for analysis and probability. I think it's better to finish the probability class and then we will change of topic. Okay. I mean, it's
Okay,
up to you. It's up to you. If you want to, if you want, we can. But I think it's the best to finish the probability part and then we will start the analysis part. Okay. So today we remain in probability. Mhm. So, any questions about the thing we did last time? No? Okay. So, last time we saw the generating function of a random variable. And just to remind you what was, the generating function is a function of z, okay? Generating function. It's g of x of a random variable x. I mean, x is a function from omega to r, and g is the expectation. Okay, if you remember what was the definition of the generating function, is the expectation of z power x. Okay, and that was simply the sum of the probability that capital X takes the value k times z power k, and this sum runs from 0 to infinity. Okay, this sum runs from 0 to infinity, so it's a power series. It's a power series, and if you remember, G is defined on the disk of center the origin and radius 1. Okay, and it goes to um, those values is C. Okay, so this is a subset of C. Is just a disk centered at the origin and with radius 1. And we take the adherence, so it's this disk. Okay. If you want to define this disk in terms of a set, is the set of complex numbers C, such that the modulus of C is less or equal than 1. Okay. Good. And we saw that this function characterized the law of the random variable. That means that all the information I can get from X, I can get it from G. Okay, so that was a theorem we finished last time. The generating function characterizes the distribution of a random variable. Okay, and yeah, we saw that also the generating function has an algebraic property. Okay, so this is also a reminder. We saw a theorem that says that if x and y are two independent integer value random variables, okay, so x goes from omega to n and y goes from omega to n. This is not the same, so it can be an omega prime, okay? Then the sum x plus y, which is also a random variable, has generating function. We can call this capital C, so the generating function of C at little z is just the product of the generating function of x, little c, times the generating function of y at little c. Okay, so this is an algebraic property. Okay, algebraic property. And you know, this is something. It should be. You maybe are familiar with some function that has this property. No, for example, the exponential function. If you have exponential of alpha plus beta, this is the exponential of alpha times the exponential of beta. Okay, so here the generating function exhibits an algebraic property similar to the exponential. Okay, and why are this type of property useful? Well, for computation. Okay, if you want to compute some things and you are working with the sum might be complicated. Okay, so if the sum is complicated, maybe in a certain sense I can just divide the two informations separately and use them separately. Okay, so keep that in mind. That's one of the properties we have to know. And the proof was very easy. Okay. I have prepared for you an exercise that will be added to the list of the exercises on probability. Uh, I hope maybe at the end of this weekend I can send you the list of exercises. Okay, so you can start working on them. And yeah. Oh yeah, I forgot here a very important assumption is that x and y are independent. Okay, if you remember, this symbol means independent. Okay, it's not really a standard symbol, okay, but it's an interesting way to abbreviate this information. Okay, I think we can continue with more advanced topics. The thing I want to discuss now is something that is called as the strong law of large numbers. Strong law of large numbers. Anyone here have heard about this law? Anyone here know what the law of large number tells us, and why is this important? No? Maybe those who were in classe préparatoire? You don't remember? Okay. Okay, no problem. It's a very, very profound theorem. Okay. So, no, Albin, c'est pas la théorie des grands nombres, c'est la loi des grands nombres. Ok? C'est la loi des grands nombres. Voilà, in French, loi des grands nombres. Okay, and it's very profound. Okay, so let's consider a sequence of events. Okay, I can call them AN for n bigger than 1, and let AN IO, okay, the set, this is by definition equal to, maybe I can move this from here to here. So let AN IO by definition is the set of little omega such that omega is in AN for an infinite number of indices n. Okay, so when I say AN infinite number of indices, what does it mean? It means that maybe I can have here A1, maybe A2 is this one, maybe A3 is this one, etc., etc., etc. And little omega is somewhere for an infinite number of indices. For example, I can say that omega belongs to A to n. Okay, it means that omega belongs to A2, A4, A6, etc. And you agree with me that this is an infinite number of indices, isn't it? So that's the definition of this notation, infinite number of indices. Okay. Any question about that? Is it the definition clear? Okay. So IO.
I have a question. What does the I? Oh, well, okay.
Infinite often. Okay. Infiniment souvent in French. Okay. Now, what does it say? The Borel-Cantelli lemma. Well, the Borel-Cantelli lemma. Okay. Maybe in red. Borel-Cantelli lemma. It says that if you have a sequence of events that are infinite often, okay, it says that the sum, okay, so maybe I can just copy this part, it's the same, copy. Okay, so I have a sequence of events, and that what appears in infinite numbers, infinitely often. Okay, take. The theorem of Borel-Cantelli says that the sum of the probability that AN is finite for n equals 1 to infinity, it's an inequality. So this is implying that the probability of AN infinitely often is 0. Okay, so we have an implication. If the sum here is finite, then the probability that AN happens infinitely often is 0. Okay, that's the Borel-Cantelli theorem. We can make the proof if you want. I don't know if it's interesting for you or not, but this is an important step in the proof of large numbers. Okay. So let me just put all the results we need at the end. So this is the first result we need to prove the law of large numbers, the Borel-Cantelli lemma. I don't know if it's interesting to prove it or not. Okay. Do you want to prove the result, or do you prefer to? I don't know if it's pedagogically important. I think it is, but okay, let's do the proof. Well, we have to make an observation. Observe that the set an infinitely often, this can be written as the intersection of the union of ak. This union goes from k bigger than n, and the intersection runs from n equals 1 to infinity. Okay? So what does it mean? This? It says that I have to take the union of all the events that are bigger than n. I take the union of them, but also I take the intersection from n equals 1 to infinity. Okay? So you may try to write this. So you have the intersection from n equals 1. You will get the union of ak for k equals 1 up to infinity, intersected then. Okay, so this intersection comes here, and then you have the union for k equals 2 of ak, sorry, of the infinity if you want. Then the intersection, and here you continue your intersection. Okay, at n of union of k bigger than n ak. Okay, the intersection, remember, is can be replaced by and the union can be replaced by or. Okay, so if an is the set of little omega such that omega is on an infinite number of sets an, okay, then I can actually write it like this. I take the union of all the events and then the intersection of all of them. And this will give me exactly and precisely the values of little omega that happens an infinite number of times. Okay? Because I take those that are here, but also those that are here. Every time you stop at one union here, you are ensuring that they are on all those AK. But if you want to recover the omegas that are in all of the possible combinations of sets, you have to take the intersection of all of them. Okay? So that's our first remark, our first observation. Now, the second one is, we can explain a little bit more here. Okay? Since if little omega belongs, okay, to this intersection, okay, then for all n bigger than 1, omega belongs to at least among one event among an plus 1, an plus 2, etc. Okay, so this is a necessary condition. It belongs at least, okay, so the keyword here is at least, in one of the events. And this thing implies that little omega belongs to an for an infinite number of indices. Okay. Now, what happens if omega n? So this is in one sense. Now, what happens if? Okay, so period. Now, if omega is in an for an infinite number of indices n, it is for all n bigger or equals than 1 in at least, okay, so we recover this at least, okay, one of the sets an plus 1, etc. Okay, so now I'm talking about the intersection. Now, if you think about the union is a decreasing function of indices. Okay, the set union for k bigger than n for an decreases as n increases. Why? Well, because I'm taking less and less people. Okay, so for example, if you have something like this, A1, A2, A3, A4, and you take the union, is this thing, and you take the union for k bigger than 1. In that case, you recover all of this. But if you take the union for k bigger than 3, you only have this part, okay? So this set, the size of this set, you are taking less and less people, so the size decreases as n increases, okay? So that's important to see what are the monotonicity of the different terms that appear here, okay? So I say that the set decreases as n increases. So do you remember that the probability of an infinitely often, this is the limit when n tends to infinity of the probability of the union for k bigger than n of ak. Okay? This is the set we say before that is decreasing. So this probability is also a decreasing function. Okay? Since the probability of a smaller set will be smaller. Okay? So if this set inside gets smaller, the probability also is a decreasing function. And if you remember that a sequence which is bounded by a constant, let's say it's bounded from below and is decreasing, then it converges. Do you remember that theorem in French? Is the theorem that says une suite décroissante et minorée converge. So, for those who don't speak French, I think those who don't speak French speak Spanish. So, in Spanish, that will be something like una sucesión que es decreciente y minorada converge. Okay? So, I can actually write this limit because it has a sense. I know it exists. Okay, I know this theorem of the monotone limit ensures the existence of the limit. Okay. Any question from that? I can continue. Okay. Now, remember that the probability, as we defined it some class now before, it has a property of sub-sigma additivity. Okay, so what does it mean? That means that this probability here will be smaller than the sum of the probabilities for k bigger or equal than n. Okay, the probability of the union is smaller than the sum of the probabilities. And the simplest case is when you have two events, A and B. The probability of A union B is smaller than the probability of A plus the probability of B. Why? Well, because this is actually equals to the probability of A plus the probability of B minus the probability of the intersection. So it's obviously less than the right-hand side. Okay? So I'm only using things you already know. Okay? There's nothing new here. I'm just mixing the different theorems you must know now. Now, I have some summability assumptions here on the right-hand side of this equality, and I know that this part tends to 0 as n tends to infinity. Okay, now that's the proof. Okay, this ends the proof. Okay, so we prove that this result, if I assume that the sum of the probabilities is less than infinity, then the probability that the event an is infinitely often appearing is 0. Okay? That's the proof. Okay? Now, the Borel-Cantelli lemma, okay, is important to say, to prove actually the strong law of large numbers. Okay, so this is the theorem, strong law of large numbers. What does it says? Well, it says that let xn for n bigger or equals than 1 an independent, identically distributed sequence, IID, independent, identically distributed sequence of random variables, okay, of 0, 1 valued random variables, okay, taking the value 1 with probability P. Okay, of course, this is between 0 and 1. Then, well, the probability of the limit when n goes to infinity of 1 over n times the sum of xk equals p for k equals 1 to n is equal to 1. Okay, so in a phrase, what does it mean? It means that, okay, it is the sequence of the mean. This is a mean. You can see the formula is just an average. Okay, so the sum of 1 over n from k equals 1 to n of xn, okay, converges almost surely to p, to p, almost surely to p. Okay, can anyone see that it actually, this theorem says something quite obvious? I'm repeating an experience here. So I flip a coin. Okay, I can get 0 or 1 when I flip a coin, and I have the probability p to at every time have the value 1. Okay, so if you compute the average of your results, then this probability will be 1. If you launch if you flip a coin an infinite number of times, and you compute what's the proportion of times that the coin is in 1, then this value converges to p. Okay, it's a very obvious thing. I'm sure you don't need this big theorem to understand that, but that's the name of the theorem. Okay, and it's actually a very important theorem. You will see later why, but yeah. Okay, any question about that, the strong law of theorem, or any other question? Okay, so yeah, just remember, if you have any question, just stop me. Okay, now, and a very important inequality in probability is the Markov inequality. So Markov was this Russian guy who actually create the Markov chains and the Markov processes. So he's a big guy, okay? And this is the Markov's inequality. We will see this inequality again on the context of analysis later, but it says something which is quite obvious. Okay, so theorem. Let Z be a non-negative real random variable, and let little a be a positive number. Then the probability that C is bigger or equal than A this quantity is bounded from below by the expectation z divided by a. Okay? So if z is a non-negative real random variable, okay, and a is a positive number, then the probability that z is actually bigger than a is bounded by the expectation of z divided by a. This has a geometric interpretation in terms um, of functions. So I don't know if you can understand it right now, but I will try to show you why this inequality is actually very, very basic. This inequality says that if you have your density, for example, of your random variable, okay, and you want to compute what's the probability that z is bigger than a, you have a value a here, for example. This is a. So the probability that c is bigger than a corresponds to this area here. Okay, this is the probability that c is equals to a. Well, this is actually bounded by the expectation of z, okay, times a. You can actually think about this inequality in the other form. It says that the expectation of z is bigger than a times the probability that z is bigger than a. So this, okay, is the area, okay. You have the basis and you have the height, okay. And it says that the expectation of this function is less, okay. So the probability that z is bigger than that is that thing, okay. And it's bounded just by the mean of the function, okay. But we will see this later again, and I'm sure you will understand, but we have to do the courses of measured theory before. Okay. Now, I can prove this inequality in a more classical way. So proof of the Markov inequality. Well, what can we say about this? Actually, a very basic thing is that if you consider the z function, so you have bigger than a times the indicator function of the set of z bigger than a. Okay. Now, if you take the expectation, taking expectations, we get that the expectation of z is bigger than a times the expectation of 1 of z bigger than a, okay, and this is actually equals of to a times the probability of z bigger than a, and that's the end of the proof. Okay, so the proof is quite straightforward. Okay, any question about that? No? Good. Do you want to do some exercises? Maybe a basic.
Yes.
So take 5 minutes to do this one. Okay. Exercise. Show that for any A included an omega and any B included an omega, okay, the indicator function of A intersected and B is equals to indicator function of A times indicator function of B, okay, and that the indicator function of the complementary of A is 1 minus the indicator function of A. Okay, now if you have that, you can prove, and then prove that prove what? Prove that the if an is a partition of omega, 1 will be equal to the sum of the indicator function of an for n bigger than 1. Okay? So now try to do this exercise, and in 5 minutes we can correct the exercise. Okay, 5-6 minutes. If you finish the exercise, just put me in the chat that you have finished. Someone has already finished the exercise. What do you mean, Alban, that you don't think it looks like something general?
No, I say that I don't think that they must be independent or not. Like we don't really care about this. We're just saying that we take A and B from omega.
Yeah, it's exactly what I say.
Yeah,
Show that for any A and any B.
yeah. Yeah. I was just answering to the question of Audrey.
Ah, okay. Sorry, I didn't see that. I had a question. I'm sorry. So what's the question of Audrey? No, yeah, you're right. They are not independent. We are not talking about probability, so remember that A and B are independent, means that the probability of A, okay, so, oops, it's not that one. A and B are independent if and only if the probability of A given B is the probability of A. That's the definition of independence. But here I am not speaking about probability. So
Well, assuming that I can't do the exercise, I just did some research, but I don't understand how to prove to show that the first line actually.
okay, we can correct it together.
Like,
Okay.
actually, my trouble is that I can't play with the indicator function correctly.
Okay. Can you please, Albin, tell me what does it means? This? What is that? What
Uh,
does it mean that?
I'm not sure I got it.
This is a function, okay? This is a function that it takes an x and it returns a value 1 or 0. 1 if little x belongs to A, and 0 if x doesn't belongs to A. Okay? It's a function. Okay? So now the exercise was prove that this equality holds. That means that prove that those two functions are the same. Mhm. How do you prove that two functions are the same? How do you prove that f of x equals g of x?
If f of a is equal to j of b.
Yeah, you can do that, or actually you can also do f minus g has to be identically equal to 0. No? In any case, we have to prove that for any value little x that I take, those two functions are the same, or I can just make the difference of both and prove it's the 0 function. Okay? Does it help you to make the exercise? Is it a little bit more clear? The exercise asks to prove this equality between two functions. Okay? So what I have to prove? I have to prove that this at little x is the same that this product at little x, and this has to be true for any x where, Alban?
In a and b.
No, in omega. Okay? In the universe. I have to prove that this equality holds since this function, the indicator is defined not on A, not on B, but on omega. And it goes to the set 0, 1. Okay, so I have to prove this equality for any little x in omega. So when you want to prove something that is true for an infinite number, well, not an infinite number, but a non-specific number of points, you start your proof by saying let. Okay, so this is the assertion and this is the proof. Let little x in omega. Okay, I want to prove that those two functions are equal, so I introduce and let h, the function from omega to 0, 1, well, it's actually 0, 1, that a little, well, it's not the same x, so it's u goes to the indicator of A intersected with B at u minus the product of this and this. Okay, so let x in omega, let h be this function. What's the value of u? So h of u, okay, is, as I said it before, this difference. Okay, and now this thing will be 1 if u belongs to A intersected and B, or 0 if u is not in A intersected and B. Okay, so this is this first part here. Now, the second part, the green one, this is one if x is in A, 0 if x is not in A. Okay, and the last one is the orange one, is 1 if x is in B, and 0 if x is not in B. So if you make a little drawing, you have here omega, okay, you have somewhere A, you have somewhere B, and somewhere you have the intersection of both. Now you take an x in this omega. It can be here, it can be here, it can be here, or it can be in the red one. Okay, so you have 4 possibilities. Let's call it this 1, 2, 3, and 4. So what's the value of h of u, of h of x, if you want, in the first case? It's not on A, it's not on B. So the red term will be 0, because it's not in the intersection. It's not in B, so it's minus 0 times 0, and you get 0. Okay? Now, what happens if we are in the second case? I'm in A. So h of x is in A, so it's obviously not in necessarily in A and B. Okay, so I'm in A, but I am not in B. So this is 0 minus 1, because I am in A, but I am not in B, times 0. So this is 0 also. Now, third case, h of x will be 0 because I am in B but not in A, minus 0 times 1, this is 0. And finally, the last case, h of x is 1 because I am in A and B, minus 1 because I am in A, times 1 because I am in B, and this is also 0. Okay, so I just proved that for any possible case of x, the function is 0. That means that those two functions are the same. Is it clear for everyone?
Yes.
Yes.
Okay.
Yeah,
Now.
it's hard to think like this.
Yeah, it's a little bit difficult at the beginning, but don't worry. With the months and the semester, you will be more confident and you will improve your skills. So I just did the first one. So maybe Elvan, do you want to try to do the second one? This one?
Yes, but I need maybe 5 minutes.
Okay. Take 5 minutes, and when you finish, you will dictate to me the reduction. Okay, the answer.
Do you want me?
Yeah. Go ahead. Tell me. Alban, are you there?
Yes, a minute, please.
Yeah.
I'm sorry, I'm trying to find the conversation, like the session with my phone to take the picture directly.
Or you can just tell me the things, and I am going to write the things you tell me. You can just dictate to me the content of what you want to say.
Ah, I just need like 2 seconds to give it to you. like for real. I just sent it. Do you have it?
Yes.
I did it the same way as you did,
Mhm.
like using H function.
Yeah, good. Okay, well, it's perfect. Perfect. So you have the proof of this result by Alban. Confer Alban. Now, the last one. Where is it? Here. Yeah. Prove that if this thing, if AN is a partition of omega, then you have this. I'm going to correct that one, okay? Okay. Proof. AN is a partition of omega. What does it mean? That means that AI intersected with HA is empty for any I different from J, different of J, and the union of all the AI for I equals 1 to infinity is omega. Okay, so essentially you are saying that if this is omega, okay, then you have A1, A2, A3, I don't know, N, okay? If I have just 4 of them, it will be something like this. So they are disjoint sets. The intersections of any two of them is empty. And when I collect them all together, I recover omega. Okay. Now, I want to understand this object. This is a function. Okay. This is a function. So this is the function equals to 1 if 0 if at x. Okay. So this is a function. We can call it j. At x is 0 if what? If x belongs to the union of ai for I bigger than 1, or 0 if x doesn't belongs to the union of ai for I bigger than 1. But remember that this is a partition, so x can be anywhere. X can be anywhere. It's in the union. Okay, so this second case never happens because the sequence of AI is a partition of omega. So I recover omega completely. That means that the only possibility is 1. So since AI 1 is a partition of omega, for any x in omega, there is there is an index. We can call it m, such that x belongs to am. And obviously, if it's in am, it's in the union of ai for I equals 1 to infinity. So g of x is 1 because this is omega. And that's the proof that if you have a partition and then you consider the sum of all the indicator functions defined on each of the sets defining the partition, then this is actually just 1. And remember that if you take this and you see what is actually this as a function on an axis, so here you have the plane, okay, and the indicator function of this one. I am not very good for drawing things, but the indicator function of this thing is the function that is equals to 1 on that region. Okay, so this is 1, this is the height 1, okay, and it's 0 everywhere else. Then you get the other one here, which is 1 only this piece, and 0 everywhere else. And you can see that if you add all the things, you recover the function which is 1 everywhere on omega. Yeah, I'm sorry for the drawing. It's not very good, but I hope you see the things. Actually, a good way to draw this thing is in dimension 1. So if you have here your omega and you consider a partition of the set, let's say in 3 terms, 1, 2, and 3. What is the indicator function of each one? One is a function which is equal to 1 in this side, then 1 in this side, and 1 at the end here. And you can see that if you do the sum of all the functions, you recover the function which is equals to 1 in all the omega sets. Okay? Is that clear?
Yes.
Okay. Okay. Perfect. Do you want another exercise or do you want to continue the lecture?
You said you're gonna send us like a work, like a paper with a lot of exercises.
Yes.
Maybe then we can continue the lecture.
Okay. But if I give you the exercises, you have to do it, okay? So play the game.
Yeah, of course.
Okay.
It's for our future.
Yes. Okay, so now we are going to start the new chapter on integration. Okay, so this is chapter 2. Measure theory. So measure theory is a general mathematical theory, and a particular case is the probability theory. Okay, so we need this because of probability, of course, but also because in machine learning, a lot of things need to be computed by integrals, and those integrals are the Lebesgue integral. Okay, so it belongs to general measure theory. The first notion here, so section 1, is measurable functions. Okay, so what measurable functions are? And again, we already defined what was a sigma field. Okay, just remember the definition of a sigma field. What was a sigma field? It was a collection of subsets on X. So let X be a set. A collection of subsets of X. We are going to denote that by I don't know what letter would be good. I don't know. What was the letter we used before to denote the sigma fields? Do you remember? I often like a like this, but I don't remember which letter we used before.
I think it was a capital F.
Ah, yeah, capital F. Thanks. Yeah, F as field. Yeah, sure. So this is a subset in the power set of X. Okay. And the first hypothesis was that X belongs to F. The second condition was that if A belongs to F, then the complementary set belongs also to F. And the last condition was that if AN belongs to F for any n in the natural numbers, then the union of those sets for n equals 1 to infinity belongs also to the sigma field F. Okay, so we already saw that. We already saw some examples of sigma fields. Now we are going to define what a measurable space is. Okay, so this is a definition. If X is a set and F is a sigma field defined on X, then we call the pair X F a measurable space. Okay, so it's a space that I can potentially measure. Okay, and if A is in the sigma field F, we say that A is a measurable set. Okay, so the sigma field contains subsets. Okay, they are denoted by A, and for those guys, I can compute something that is a measure. I can compute their size. Okay, good. Now, I'm going to need the definition of a topology here. Okay, so topology. We say that a topology on X is a collection of subsets of X denoted by T. Satisfying again three properties. The first one is that the empty set belongs to the topology T, and X himself belongs to the topology T. Now, second condition is that for any O1, O2 in T, the union O1 union O2 is in T. Okay, so it's stable by union. We say that a topology is stable by union. And three, we have that the intersection of a finite number of sets is in O. Okay. For any O1, O2, On belonging to T, then the intersection for I equals 1 to N of OI belongs to T. Okay, so this is the definition of a topology. Anyone knows why this notion is interesting? Why topology is important? Have you heard before about topology?
Yes, a bit.
Yes, a little bit, but 2 years ago, 1 year ago, not.
What can you tell me about topology? Why topology is important, and for what it is important?
Good question.
I think it allows us to represent in some dimensions elements and see if they are joined or not. No.
Yes, that's one of the applications, but I would say that I don't know. I don't have it here. It's maybe because I am using it
Can
in
I
microphone.
Can I try? Like with the topology, if I define some parameters for one shape and some other parameters for another shape, I know that I will never be able to transform one into the other. So finally, it's kind of defining the basics and
Okay.
the difference between them.
Yes. Well, you are true. You're right with all the things you say, but maybe the most important thing is that topology allows us to define limits. Okay, the topology allows us to define limits. You know, in analysis, the central notion of any of the concepts you encounter in analysis, they are defined in terms of limits. Think, for example, about the derivative. How do you define the derivative of a function? As the limit when h goes to 0 of f of x plus h minus f of x divided by h, isn't it? And how do you define the integral? The integral of a function when you integrate, I don't know, between a and b. This is also defined as the limit of a sum of rectangles. Okay, when the basis of the rectangles dx tends to 0. Huh? Do you remember here, if you want to integrate this function, you take rectangles here and you say that this basis dx goes to 0, and you approximate better and better the area under the curve of the function. So the derivative is a limit, the function is a limit, but also the convergence are limits. What does it mean if I have a sequence of function fn converging to f simply convergence? Well, that means that the limit of f of x minus fn of x as n tends to infinity is 0. And also when you were at second year, you saw the uniform convergence. And what does it mean? It means that the limit of the supremum number of the absolute value of fn of x minus f of x for any x in the interval you are considering your function tends to 0 as n tends to infinity. Okay, so all the concepts in analysis are defined in terms of limits. So it's very, very important to know what limits are and how they are defined. Okay, and the key notion that allows us to understand limits in a formal way is topology. Okay, so a topology is a set containing subsets of x satisfying those three properties. Huh? Now, I'm going to ask you if you consider the set x equals ABC. Can you please give me a topology on this set? An example of topology defined on this set.
Would be a triangle.
Yes. What do you suggest for a topology on x? X equals ABC.
Like as ABC are dots, and X is a set of dots.
Can you repeat it, please?
Like I assume that, for instance, A, B, and C are dots, and X is just a set of 3 dots, so it
Yes.
could represent a triangle.
And what's the topology you are suggesting?
This is like a plan.
A topology is a set of things. Okay, so you have a 1 or 2. So you have to tell me what's a 1 or 2 or 3.
The segment, the size, the segment, the distance between A and B, and then B and C, and then C and A. Or the angle between AB and AC, then BA and BC.
You say the angle?
No,
Tu as dit l'angle?
Yes. I consider.
No. There's nothing about angles. Okay. For example, I can suggest you one topology: empty and ABC. Okay. So I suggest you this. Is this a topology on X? You have to verify those 3 conditions. So if X is ABC, I say T, the topology is empty and X. Is this a topology on X? So you have to verify the first condition, the second condition, and the third condition. Are those conditions satisfied by this topology?
The first one is satisfied
Yes.
because, well, it contains the empty set, and
Mhm.
well, X is the set ABC. The second one, I'd say that the union of the empty set and X, well, makes X, so it's stable.
Yes.
And the last one, I don't know how to prove it.
Well, what's the
Yet.
intersection? What's the intersection between the empty set and X?
It's X too.
What's the intersection between empty and X?
X.
Empty.
No.
No, it's nothing. Yeah, Alban is right.
And is empty set inside T?
Yes.
Yes. Okay. So it is. It is inside. Okay.
Okay.
So this is one example of topology. Okay. Do you have another one, maybe? Another one to suggest on this set?
Empty set.
Yes.
The set AB and the set C.
Okay. A, B, and C. So, okay, so we have this suggestion of our colleague who want to try to see if the example he gave us is actually a topology. Audrey, do you want to try? Want to try to see if this is a topology or not? You only have to verify the three conditions and see if it's good or not.
If no one, I can.
Yeah, please.
So the first one is not satisfied because X is not included in T.
Yes. Okay. So this can't be a topology because X is not inside. So we may try to improve this proposition from even to something that has some chances to be a topology. So if I add X here, okay, now the first condition is satisfied. Can you please, Alban, continue and try to see if the second one is satisfied?
So now I'll take them 2 by 2. Okay, so let's call them empty set is first item, right? And X gonna be the fourth. So if I take the first and the second item, the union between them is empty set, and it's going to always be empty set. So it's going to be 5.
The union
Oh
is
no,
not.
the union is empty.
No, the union between the empty set and AB is AB.
Okay, yeah. So AB is verified, and if I do the same with the first item and the third one, it's going to be the same. Then if I take AB and C, the union is ABC and it's X. If I take AB and X, the union is X also, so it's good.
Yes.
So it's going to be the same with C.
Yes. So you have to take all the combinations of two elements. So you take the empty and this, the empty and this,
So
the empty and this.
Yes, it is.
This and this.
Union.
So the second condition is satisfied. Everyone agrees that the second condition is satisfied? Is it clear for everyone? If not, please tell us. Okay, I think it's clear for everyone. Now, Albin, the last condition, the intersection.
And finally, for the intersection, I need to verify the intersection of all of them at the same time. Um, so the intersection of the four items is the empty set
Mhm.
and is a part of T. So finally, the T is a topology.
Mhm. Okay, good. So we have another example of topology here, okay? And you see, inside the topology, you have sets. You have this, and this, and this. The elements of the topology have a name. They are known as open sets. Okay, so here, remark, the elements of the topology are known as open sets. In French, you say ouvert. Les éléments d'une topologie sont des ensembles qu'on appelle ouverts. Now, we gave two examples of topology on the same set X that was ABC. So we have two possible topologies. We have this one and we have this one. Okay. The second one has more open sets than the first one. We are going to say that the second one is finer than the first one. Okay, so that's a definition. If T1 and T2 are topologies on X, then, well, not then, but such that T2, T1 is included in T2, we say that T2 is a finer topology. Okay, finer, so you have more open sets. Is it important? So, if you want to define limits, okay, what do you think is important, to have more open sets or to have less open sets? Remember that topology will allow us to define limits. Okay? So, what do you think is better, to have more open sets or less open sets?
Less,
Why?
because it's less complicated.
Well, actually, the answer is a mix of two. If you want a good topology, you will need something that has a large enough number of open sets, but not too large, but not too, but not enough. Okay, because the look, for example, here, if I have X, A, B, C, the first topology has only two open sets, and the open sets will be used to define the points where I can go as a sequence. They will allow me to define limits. So if I only have two of them, empty and X, the only limits that are possible are X. Okay, I can define differentiate those points. Instead, if you take this topology, A, B, C, X, and E empty set, now I can actually distinguish between converging to C or not, because I have an open set containing C. So now I can have another topology here. For example, if you say T is something that contains A, B, C, okay, I want that A, B, and C are open sets. Now, if I add the empty set and X, can anyone tell me if this is a topology or not?
Yes, it is.
Well, no, it's not, because the union of this is not in T. Huh?
Okay, my bad.
So this is not a topology. We are going to add those guys. We are going to add people here to ensure that it is a topology. So I have to add more people there. I have to add AB. I have to add AC. And I have to add BC. Now, is this a topology?
Yes.
No. What do you think, the others? Why you say no?
Because if I take AC and C, oh yeah, AC gonna be, yeah, no. Yes, it is.
Okay. Okay, so the union of any two of the elements has to be inside. For example, here the union of those two gives me X, and the union of, I don't know, this one and this one gives me X also. Okay. Now, what about the intersection? If I intersect, for example, this one with this one, I get that one. Okay. And if I intersect that thing with that thing, I recover that thing. Okay. So this is a topology T3 maybe, which is larger than the two before we saw. So this topology contains more open sets. Okay. And since it contains more open sets, this topology will allow me to distinguish the points sufficiently well to compute limits. Okay, so here I have A, B, C, and my topology is A, B, C, but also AB. I don't know if I have enough colors. AC, and BC. BC, and of course omega, which is X here, and the empty set outside. Okay, so this topology will allow me to define limits to A, limits to B, limits to C. Okay, so that's very important. Depending on the topology you have defined on that set, you will derive different notions of convergence. Okay, any question about that? Is it clear enough for everybody? Okay, good. Now, topology is a very, very general way of thinking about things. And we have to define what's the convergence of a sequence of points in a topological space. Okay, so definition of convergence in the topological sense. Definition of convergence in the topological sense. So let xn n bigger than 1 be a sequence of points in a topological space xt. So X is the set TSD topology. We say that the sequence Xn is convergent if, okay, what? If there is an open set O in the topology such that for any n, such that, sorry, there exists integer n in n such that for any n bigger than n, the term xn belongs to the open set O. Okay. Now, what's the picture you have to have in mind? You have things like this. Here you have O. And here you have the sequence. X1, X2, X3. Okay, so there is a moment, and that moment is capital N. There is a moment, and there is an open set such that later, starting from capital N, all the points of the sequence are contained in the open set O. Okay? So that's the notion of convergence in the topological sense. Okay? I'm going to say that this sequence is convergent if I can find an open set of the topology such that there is a moment called n, such that after that moment, any point of the sequence belongs to the open set O. Okay? Is it clear? So that is the definition of convergence of a sequence of points in a topological space. Any question about this? No? Okay, good. Now, that's why we can say that in this case, in that case, we can write limit when n tends to infinity of xn. Okay, good. Now, topology is very important for that. Okay, open sets are the elements of the topology, and we have also to say that, remark, if O is an open set, the complementary of O is closed, is said to be closed. Okay, so an open set is an element of the topology, and if the complementary of O and the complementary of O is said to be a closed set. Okay, is it clear? Now we can take this example as before, and I'm going to ask you something. So, for example, Ivan, tell me, is this set open?
Yes.
Yes, good. Now, Albin, can you please tell me if AB is closed?
I want to say yes. I don't know why.
Yes, it is. Why? Well, because what's the complementary of AB?
MZ and C.
No, it's C. Okay. The complementary of this is C. But C is already in T, so it's open. Okay, so we just say that AB complementary is open, so AB is closed. Okay, from this you can see that actually being open and being closed are not mutually exclusive notions. We can be open and not closed. We can be open and closed. We can be closed but not open. And we can be neither open nor closed. Okay? We're going to talk more about this later. But just remind that open is not the opposite of closed. We can be both, as said, at the same time. Okay, so here is yes. and here is yes also. This is an example of set that is at the same time open and closed. Okay, good. Now, any questions on that?
Closed is only defined as the opposite of open?
As not the opposite, is defined as the complementary
Oh,
of
yes.
an open set.
Okay.
Yeah.
Thank you.
Okay. Any other question about that? No? Good. Now, if you have functions between topological spaces, you can define continuity. Continuity. Okay. And here you say, let x t and y ty be two topological spaces and f a function from x to y. Okay, this is a function. We say that f is continuous. Okay, we say that f is continuous if what? For any open set in Ty, okay, for any O in Ty, the inverse image of O belongs to Tx. Okay, so here you have X, here you have Y, you have different topologies in each one. Okay, topology on X, and you have a topology on Y. And we are saying that if you take any of those guys here, for example, that one, this is O, then the inverse image of F is another open set for the other topology. That's the definition of continuity. Okay? And this is very, 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 very important because we are going to say that two topological spaces are homomorphic if we can find a function f which is one-to-one and continuous with the inverse which is continuous. Okay. Okay. Any question on continuity? Is it clear for everyone what continuity means?
Can you do an example by writing formulas and not only the representation on space?
Yes, for example, if you take f, the function from R to R, that from x gives x squared is continuous. Since the inverse image of the interval AB, what's the inverse image of the interval AB? If you take the square function. So AB is here. What's the inverse image of AB?
It's the square root.
Yes, but it's the inverse image of a set is a set, so I need an interval here. What's the inverse image of that interval?
It is
Square
an
root A, square root B.
Almost.
It is an union, right?
Yes, of what?
Of square root A and square root B union square root minus A square root minus B. No, E minus, no, I can't say. Yeah, I'm sorry.
Okay, and this thing is open. So f is continuous. Okay, now maybe we can give an example of something that is not continuous. Okay, the indicator function of the interval 2, 3 is not a continuous function. Why? Why this function is not continuous?
Because it's injective.
Because what?
No, I'm sorry. I don't know.
We need to find an interval here which will be an open set such that the inverse image of that set is not open. Okay, and of course you can see that the problem is in this region 2 and 3. So for the next time, try to find here an interval. I mean, it's quite obvious, okay, such that the inverse image of that, you have to compute it, okay, you have to give it in this way, will not be an open set. Okay, well, so that's continuity. And actually here, I'm sorry, I did a big mistake myself. This is not open, this is closed, so I have to correct that here. I'm sorry, I took here a closed set. It's the same, but the brackets are in the opposite side. Well, in English, in the UK notation, we use parentheses to indicate open sets. So I'm going to restrict myself to that notation. So this means open sets. I put close intervals here. In French, you use brackets to say it's closed in one sense and open in the other one, but in English you use only brackets for closed sets and parentheses for open sets. Okay, so those are parentheses, those are open sets. Okay, good. So that was continuity, and now we can define homeomorphisms. So this is a definition. Let x and y be two topological spaces and let f from x to y be a bijective. In English, we can also say one-to-one function such that f is continuous and f minus 1 is also continuous, okay, let x and y be two topological spaces, be bijective such that it is continuous, then f is called a homeomorphism and x and y are homeomorphic spaces. Homeomorphic spaces. Okay, so the fact that two topological spaces are homeomorphic will imply that they share a lot of common properties. Okay, in particular, if you have a sequence of points on X that converges to a point, then the image will also converge on the other topology. Okay, is it clear? So that's a result here, theorem. If Xn is a sequence, is a convergent sequence on XTX, and f from x to y is an homeomorphism, then the sequence f of xn is convergent in y ty. So if I take my image here, the same as before, I copy the image, I paste it here. I have a convergence sequence in which color can be good here, this one. I have a convergence sequence here. Well, that implies that here my sequence will be also convergent if f is a homeomorphism. So I need continuity and bijectivity. Okay? Is it clear for everyone? So what's the important thing about this lesson? Topology is defined in terms of open sets. I can have different topologies defined on the same space. A topology allows me to define limits and convergence, and the convergence depends on the topology. So if I have different topologies, they define different notions of convergence, and we need, for working, a topology that contains a large enough number of open sets, but not too many, but we have to be something in the middle. Okay, we have to have enough open sets, but not too much. Okay, enough to distinguish points of interest, but not too much such that the convergence is trivial. Okay, is it clear for you? Any question on that? So if you want, instead of taking the break now, we can just continue and we will finish the class a little bit earlier. Okay. Okay. So this is a very important chapter. Okay. So please, you have to study everything we saw until now. First thing, probability. What's a probability? We saw also the conditional probability. We saw also the expectation of random variables, conditional expectation, Bayes rule, total causes probability formula. Well, we saw a lot of things, okay, and it's just the beginning, okay. So please take the time to study. Math is a very important. It's one of the essential grades you have this year, and it's the same for the next year, okay, because you have something like 72 hours of machine learning with me, okay. So I think I am the teacher you see the most, I'm almost sure. So math is a super important topic, okay. Any question until now? No?
I guess we need to practice.
Yeah, I guess, yeah. I guess. So maybe we can try to do some exercises, okay, and see if you are able to do them. What do you think? Um, yeah. Um, hmm, let me check what exercises I have already here for you. Maybe that one is easy to start. Okay, so this is the type of exercises you are able to do now. So exercise. An urn contains 15 red balls, okay, and 19 white, okay. Balls are drawn in succession at random and without replacement. So question, what is the probability that the two first are red? Okay. And now question number 2. If you have n balls numbered that urn contains n balls numbered from 1 to n. Okay, so you have number 1, number 2, number 3, n. What is the probability? Okay, so I take simultaneously n of them. I throw simultaneously lowercase n balls of the urn, what is the probability that the lower number is k? Um, are the question clear? Hmm? Is the exercise clear for everyone?
I think so.
Okay.
Yes.
Okay, so please go ahead.
I'm sorry, is it 12 at the end of the second question?
No, it's k.
Okay, okay.
if you have the answers, just post it on the conversation so I can know you have finished. Okay, so Mr. Camara have finished. We can correct the exercise and see if you have the correct answer, okay? So the first thing you need to do is to represent the situation in such a way that it will be easy for you to think about what happened. So here we have a total number of 15 plus 19 balls. Okay, so that is 24 balls. Okay, some of them are white, some of them are red. Now, if omega,
Isn't it 34?
Yes, 34, not 24.
oh yeah, you're right. Thank you. 34. Thanks. So omega is the set of those balls. Okay. Now the cardinal of omega is, as you said, 34, and I am taking consecutively two of them. So I'm making a word of two letters, and for the first one, how many choices I have? Well, I have 34 choices, and for the second one, only 33. So the total number of words of two letters with 34 possible choices for the first one and 33 for the second one is the product. Okay, so you get 34 times 33. Now I want that the two of them are red. So in the first case, I know that I have 15 red balls. So here I have 15 possible positive cases, okay, among 34, okay, and for the second one, it depends on the result of the first one, okay, so you can make a tree containing the result of the first. It can be red or it can be black, black, red, and then black, red, black, red. So for the black thing, I have how many? 19. Oh, sorry, it's white, not black. Well, anyway, we don't care. It's the Well, I say black even if it's white. Okay. I have 19 of them, I think. Yes. So this is 19 over 34. This is 15 over 34. And then how many blacks do you have given that you already have a black? So you have 18 among 34. How many reds given the fact you have the first one black? Well, 15 over 34. Okay. Now,
Sir,
yes.
isn't it 18 sur 33?
Yes, that's the thing I was looking for. 18 sur 33. Thanks. Oops. Yeah, because I get out one of them. And here I have 15 over 33. Thanks. And for the second one, if it was red, I have 19 over 33 and 14 over 33. So the probability of getting red is 15 over 34 times 14 over 33. Anyone can give me the number you get?
Yeah, it's 0.187.
Okay, good. Thanks. Is the correction of the exercise clear for everyone?
Yes.
Okay. Now, the second one. Who finished already the exercise?
Apparently no one.
Okay. So here the question is, okay, you have to define random variables. Let xi be the random variable giving the result of the ith um, um, the ith ball drawn from the collection. Okay, and the question is the probability of the minimum of xi for I between 1 and n equals k. Okay, so that's the question you want to answer. You take n balls randomly and you want to know that to fix k, of course. Okay, k is fixed from the beginning, and you want to know what's the probability that the minimum value of the balls is k. Is the question clear for everyone? Now,
Yes.
you can think in terms of a particular k value. What happens if k is equals to 1? Okay, what's the probability that the mean? I'm going actually to define a new random variable c. C will be defined as the minimum for e from 1 to n of xi. Okay, so my question is, what's the probability that c takes the value 1? Okay, so you take n of them. You are constructing a word of length n. Okay, and what are the possible values of those? Well, you have capital N balls, so this is a number, okay, between 1 and n. Okay, it's xi. Okay, xi is a number between 1 and n. Okay, now you're taking numbers inside. Okay, it can be any one of those, and you say, okay, I'm just looking at them and taking the minimal value. What's the probability that this value is 1? Okay, well, if you want to be equals to 1, that means that this implies that, well, maybe without the probability actually. If z takes a particular value, actually I can say this in general, if z equals k, that means that xk was present, I mean not xk but k, the ball k was present. Okay, so you have to mix those informations and try to find a way to think about the minimum of those functions. Okay, anyone has a suggestion of how to implement this reasoning on those random variables? You can think instead in terms of words or in terms of trees. Okay, you can select any one of those two you prefer. And for example, I can help you a little bit. The result of the first ball can be 1, 2, 3, n. And what's the probability that is 1? Well, it's 1 over n. The probability to be 2 is also 1 over n. And the probability that is the nth ball is 1 over n. Then you repeat the experiment. Okay. And as before, it will depend on, it's for example, 1 over n minus 1. Okay, and you repeat until you get the nth result. So this is the first, second, nth, and you want to adopt that the minimal value is k. That means that you have to look inside the tree, those regions, those lines containing somewhere the ball k. Isn't it? Does it make sense for everyone?
Yeah.
Okay, so I have a meeting just after, so keep this idea, try to figure out how to draw the different trees, and if you find the solution today or later, you can send it to me, and in any case, if you want, we can correct it next time. Let me just check when is the next time. Ah, no, it's not here, sorry, it's here. So
It's tomorrow afternoon.
tomorrow afternoon. Okay. Okay. Yeah. So we can see that tomorrow. Okay.
Okay.
After this class, can you send us the notes?
Yes. Right now. Okay. Well, have a nice afternoon and see you tomorrow.
Thank you. You too.
Thank you.
You too.
Thank you.
Bye.
See you tomorrow.
Bye.
See you, Mario.
Sure, bye.
Thank you.